Hello everyone, welcome to the new topic on classical mechanics, that is Hamiltonian dynamics. We have already studied the Lagrangian dynamics in the previous chapter, and in this unit we will study the Hamiltonian dynamics. Here, in Hamiltonian dynamics, the description of motion is done using generalized coordinate and the generalized momentum. This Hamiltonian dynamics is actually an alternate formulation like the Lagrangian dynamics. In Lagrangian dynamics, we have used the generalized coordinates and the generalized velocity to describe the equation of motion. That is, basically Lagrangian is a function of the generalized coordinate and the generalized velocity. But this is a new approach where we are using the generalized coordinates and the generalized momentum. We know the Lagrange's equation d by dt of dou L by dou q k dot minus dou L by dou q k equal to 0. This is the Lagrange's equation and we can see it is a second order differential equation. Lagrange's equation is a second order differential equation. Now here L is equal to T minus V. What is this? T is the kinetic energy and V is the potential energy. L is equal to T minus V, and we will say L is the Lagrangian. And this Lagrangian L is a function of QK dot and T. That is, Lagrangian is actually a function of the generalized coordinates, generalized velocity and time. Qk is the generalized coordinates, Qk dot, that is the generalized velocity. Now let us see what is this Hamilton dynamics means. We can say that this Hamilton dynamics or Hamiltonian dynamics is an alternate formulation like the Lagrangian dynamics. The Lagrange's equation, which is a second order differential equation. Hamiltonian dynamics is an alternate formulation like the Lagrangian dynamics. But comparing to the Newtonian or the Lagrangian mechanics, Hamiltonian dynamics has some advantages. Now we have seen that the Lagrange's equation, which is a second order differential equation. But the Hamilton's equation of motion that we will see later, which is a first order differential equation. So it is easier than Newtonian and Lagrangian mechanics. The advantage of Hamiltonian dynamics is that it is easier than Newtonian and Lagrangian dynamics. And these Hamilton's equations are first order differential equations that can be solved easily. Hamilton's equations are first order differential equations. Later, we will see what is Hamilton's equation of motion. So this Hamiltonian, this is basically a function of generalized coordinate and generalized momentum. So what is this Hamiltonian H? H is a function of the generalized coordinates and generalized momenta. So we will represent it as H is equal to H of QK, PK and T, where QK, which is a generalized coordinate, and PK is nothing but the generalized momentum corresponding to that particular coordinate QK. Hamiltonian H, which is a function of QK, PK and T. But Lagrangian is a function of QK dot and T. Now let us see what is meant by this generalized momentum and cyclic coordinates. The Hamiltonian function H contains generalized momentum. So let us see what is meant by this generalized momentum and another important term, which is a cyclic coordinate. What is meant by cyclic coordinates? First of all, let us see what is meant by cyclic coordinates. Then we will see what is the generalized momentum. We can define the cyclic coordinates in the following way. That is, if Lagrangian function does not contain a coordinate QK explicitly, then the generalized momentum PK is a constant of motion. Now the coordinate QK is called cyclic or ignorable coordinate. This is how the cyclic coordinate is defined. That is, if the Lagrangian function does not contain a coordinate QK, then the corresponding momentum is a constant. Then that coordinate is called a cyclic. Now it means that if some QKs are absent, for example, if some QK are absent in Lagrangian, how we can write Lagrangian, it is QK dot T, and out of this QK, if a particular QK is absent in the Lagrangian, then the momentum that is corresponding to that missing coordinate, which is a constant, that is PK is constant. If it happens, then that coordinate which is absent in Lagrangian is called cyclic coordinate. Now another term is the generalized momentum. What do you understand by this generalized momentum pk? Okay, to understand this generalized momentum, consider a simple case, a particle that is moving along the x-axis. A particle is moving along the x-axis. Suppose its mass bm and it is moving with velocity v. It is moving with velocity v. Let m be the mass. And it is, suppose it is moving with velocity v along the x-axis. Then we can say let v be the velocity. Now we can say that the kinetic energy of the particle, that is T is equal to half mv square. This is equal to half m x dot square because x dot equal to dx by dt, that is velocity. So this is half m x dot square. This is the kinetic energy of the particle. And now let us suppose that V of x be the potential energy. Suppose the potential energy be V of x. Now we can write the Lagrangian as L is equal to T minus V, that is which is equal to half m x dot square minus V of x. That is Lagrangian is kinetic energy minus potential energy, half m x dot square minus V. Now what is the momentum of the particle? The linear momentum of the particle. We know that it is mv, that is mx dot. Now we can arrive at this expression by using dot t by dot x. Since t is equal to half m x dot square, dot t by dot x is mx dot, that is px. Also we have written the expression for the potential energy which is equal to V of x. That is the potential energy depending upon x, not x dot. Therefore if you take the derivative, dou v by dou x dot is equal to 0. Dou v by dou x dot equal to 0 because the potential energy is a function of x only. Potential energy does not depend upon the velocity. So dou v by dou x dot which is equal to 0. Now we can write this expression px as that is nothing but mx dot, the momentum, that is dou t by dou x, dou t by dou x dot minus dou v by dou x dot. We can write like that because dou v by dou x dot equal to 0, and this is nothing but dou by dou x dot into t minus v, or dou L by dou x dot. That is the momentum px, that is equal to dou L by dou x dot. This is an important result, that is the momentum px, that is dou L by dou x dot. This is because the potential energy is independent of velocity. Now we can extend this idea to the generalized momentum. Suppose pk is the generalized momentum corresponding to the coordinate qk. Now we can write this generalized momentum as or the generalized momentum corresponding to the generalized coordinate qk as, we can write pk, that is equal to dou L by dou qk dot. This is the relation connecting the generalized momentum and the Lagrangian. Pk is equal to dou L by dou q k dot. This momentum, we will say this is the generalized momentum or conjugate momentum or canonical momentum. This is equal to the generalized momentum or conjugate momentum or canonical momentum. Pk is equal to dou L by dou qk dot. Now let us come back to the concept of cyclic coordinate. What is cyclic coordinate? If a coordinate is absent in Lagrangian, then the corresponding, the generalized momentum is a constant of motion. We know that the Lagrangian is a function of qk dot and t, and you assume that some qk is not present in the Lagrangian. First, let us write the Lagrange's equation. Let us write the Lagrange's equation. That is d by dt of dou L by dou q k dot minus dou L by dou q k, that is equal to 0. That is equal to 0. Now you assume that, suppose the Lagrangian L is equal to, which is a function of qk dot t, does not contain a coordinate qk. Okay, you assume that the Lagrangian does not contain a specific coordinate qk, then we can say dou L by dou qk is equal to 0. If a coordinate is absent in Lagrangian and if you take the derivative of Lagrangian with respect to that coordinate, then that is equal to 0. Therefore, what happens to our Lagrange's equation 1? That is d by dt of dou L by dou q k dot, that is equal to 0. This implies that dou L by dou q k dot, which is equal to constant. We have already proved that this dou L by dou q k dot is nothing but the generalized momentum. So we can conclude that if a coordinate qk which is absent in Lagrangian, then the corresponding generalized momentum pk is constant. Pk is constant. That is how we defined the cyclic coordinate earlier. Now we have proved that if a coordinate is absent in the Lagrangian, then the corresponding momentum is a constant of motion. That is, pk is constant here. If qk is absent in Lagrangian, then pk, which is constant. So we can write it like that. Thus, if Lagrangian does not contain a coordinate qk, then the corresponding generalized momentum, pk is constant. Or constant of motion. Thus, if Lagrangian does not contain a coordinate qk, the corresponding generalized momentum pk is a constant of motion. Then that coordinate qk, that is called cyclic coordinate. Now, so far we have discussed about the generalized momentum and the cyclic coordinate. Now there is one more point. Let us write the Lagrange's equation one more time. That is d by dt of dou L by dou q k dot minus dou L by dou q k is equal to 0. Now already we have proved that the generalized momentum pk is nothing but dou L by dou q k dot. Now substitute the value of dou L by dou q k dot in the Lagrange's equation. We will get d by dt of pk minus dou L by dou q k dot equal to 0. Okay. That is d by dt of pk minus dou L by dou q k dot equal to 0. What is d by dt of pk? It is nothing but pk dot. Hence we can say pk dot, that is equal to dou L by dou q k. Dou L by dou q k. Thus we have an equation for pk and pk dot in terms of Lagrangian. Now let us conclude. let us conclude this section. That is, the generalized momentum Pk is given by dou L by dou Q K dot. Then what is Pk dot? Pk dot is nothing but dou L by dou Q K. Then the next is the definition of cyclic coordinate. That is, if Qk is cyclic, then we have already seen that Pk is constant. So let us summarize the previous section by these two sentences. That is, Pk is equal to dou L by dou Qk dot. Pk dot is equal to dou L by dou Qk. And if Qk is cyclic, then the corresponding momentum is constant. To understand the concept of cyclic coordinate, let us do a problem. The Lagrangian of a particle moving under central force is given by L is equal to half m r dot square plus r square theta dot square minus v of r. Show that angular momentum of the particle is conserved. Here, this is the Lagrangian which corresponding to a particle moving under central force. And we have already studied that when a particle moves under central force, the angular momentum is conserved. Now we have to prove this using the idea of cyclic coordinate. We can easily prove this concept using the idea of cyclic coordinate. First of all, let us see which coordinate is missing in Lagrangian. We know that the Lagrangian is a function of Qj or Qk, Qk dot and T. And in the present case, in the present scenario, Lagrangian contains three coordinates, that is r, r dot and theta dot. This is evident if you observe the Lagrangian that is given. This Lagrangian contains only r, r dot and theta dot. Then which coordinate is missing there? The missing coordinate is theta. That is the Lagrangian function, that is the Lagrangian function given does not contain the coordinate theta. Then from the definition of cyclic coordinate, when theta is absent in Lagrangian, then the corresponding momentum, that is p theta here, that is constant. Now how do you find p theta? P theta is nothing but dou L by dou theta dot. Dou L by dou theta dot. You have the Lagrangian half m r dot square plus r square theta dot square minus v of r. Then dou L by dou theta dot, that is p theta, that is mr square theta dot, which is nothing but mr square omega. Mr square omega. That is in our Lagrangian, theta is absent. Therefore, we can say that the p theta, which is constant, p theta is dou L by dou theta dot, that is nothing but mr square omega. What is mr square omega? Which is nothing but the angular momentum, okay, which is constant. P theta equal to constant means mr square omega is equal to constant, that is angular momentum is conserved. Now let us define the Hamiltonian function. So far we have seen Hamiltonian is a function of generalized coordinates, the generalized momentum and t. Then what exactly is the Hamiltonian function h? H is basically, it is a function of qk, pk and t, and the exact equation is h is equal to sum over k pk qk dot minus L, where L is the Lagrangian, pk is the generalized momentum, h is equal to pk qk dot minus L. In the next section, we will see how to prove this equation. We can define the Hamiltonian function as sum over k pk qk dot minus L, where L is the Lagrangian. Next is the derivation for the expression h. We will arrive at the above equation, sum over k pk qk dot minus L. So how can we arrive at that equation? The derivation of expression for the Hamilton function h, the Hamiltonian function h. Let us start from the Lagrangian. We know that Lagrangian is a function of qk dot and t. L is equal to L of qk dot and t. Now what is dl? We know that dl is equal to sum over k dou L by dou qk dqk plus sum over k dou L by dou qk dot dqk dot plus dou L by dou t into dt. Take the partial derivative. Now divide it by dt, then dl by dt, which is equal to sum over k dou L by dou qk dqk by dt plus sum over k dou L by dou qk dot dqk dot by dt plus dou L by dou t. Now we have seen that from Lagrange's equation, what is this dou L by dou qk? How can you write this dou L by dou qk? The Lagrange's equation is d by dt of dou L by dou qk dot minus dou L by dou qk is equal to 0. Okay, and from that we can say that dou L by dou qk, this is equal to d by dt of dou L by dou qk dot. Okay, now substitute the value of dou L by dou qk in the above equation. Substitute the value of dou L by dou qk in the above equation. Let us write it as equation number 1. the value of, if we substitute the value of dou L by dou Qk in equation number 1, we will get dl by dt, which is equal to sum over k. Now substitute the value of dou L by dou Qk. That is d by dt of dou L by dou Qk dot, then dqk by dt plus sum over k dou L by dou Qi dot dq I dot by dt plus dou L by dou t. Now we can write this dqk by dt as qk dot for simplifying the equation. We can write the dqk by dt as qk dot in equation 2. Now dl by dt becomes substitute dqk by dt, which is equal to qk dot in equation 2, then dl by dt is equal to sum over k d by dt dou L by dou Qk. The next term is Qk dot plus sum over k dou L by dou Qk dot into dqk dot by dt plus dou L by dou t. Now we can club the first two terms. That is nothing but d by dt of qk dot dou L by dou Qk dot. That is actually the expansion of the single term d by dt of qk dot dou L by dou Qk dot. We can club that two terms like this: sum over k d by dt qk dot dou L by dou Qk dot. Okay, plus dou L by dou t. That is basically dl by dt. Now let us rearrange the expression. Let us rearrange the terms in the following way. Just rearranging the equation, nothing else. That is dl by dt minus sum over k is d by dt of dl by dt minus sum over k d by dt of qk dot dou L by dou Qk dot, that is equal to dou L by dou t. Okay. Let us rearrange the terms one more time. That is sum over k d by dt of qk dot dou L by dou Qk dot minus dl by dt. Minus dl by dt, that is equal to minus dou L by dou t. We can write like that. Now, in the first two term, d by dt, we can take d by dt outside. That is, you can take d by dt outside the summation. D by dt sum over k. Then that is qk dot dou L by dou q k dot minus L. Okay, with a common bracket. That is equal to minus dou L by dou t. Okay. We have already proved that the generalized momentum pk is nothing but dou L by dou q k dot. We have proved. Now to substitute the value of pk in equation 3. The value of pk in equation 3, then equation 3 becomes d by dt of sum over k qk dot then dou L by dou q k dot is nothing but pk. So it is qk dot pk minus L, that is equal to minus dou L by dou t. Okay. Or we can say that d by dt of sum over k pk qk dot minus L, that is equal to minus dou L by dou t. Now the things which is inside the bracket, that is sum over k pk qk dot minus L, which is nothing but the Hamiltonian function h. So h is equal to sum over k pk qk dot minus L. This is the expression for the Hamiltonian or Hamiltonian function, that is equal to sum over k pk qk dot minus L. Thus, if you have the Lagrangian, then you can obtain the Hamiltonian from the equation sum over k pk qk dot minus L. Now let us see the next section, which is nothing but the conservation of energy. What is the physical significance of Hamiltonian? Hamiltonian is basically a function of qj, pj and t, and it is written as sum over k qk dot pk minus L. Now, to understand the physical significance of Hamiltonian, let us consider the situation. Consider a conservative system. Consider a conservative system where the potential energy V, which is independent of velocity, and also the potential energy does not depend upon time explicitly. You consider a conservative system where the potential energy is independent of velocity and does not depend upon time explicitly. Now, in this scenario, let us write the Hamiltonian function. H is equal to sum over k pk qk dot minus L. Sum over k pk qk dot minus L. Okay. What is pk? Pk is nothing but the generalized momentum. We have already proved that it is dou L by dou q k dot. Now, can we write it as dou by dou q k dot T minus V? Because L is equal to kinetic energy minus potential energy. So we can write it like that. Now, it is equal to dou T by dou q k dot minus dou V by dou q k dot. Okay. Since the potential energy, which is independent of velocity, that means it is independent of qk dot, then surely dou V by dou qk dot is 0. Dou V by dou qk dot becomes 0. Now, your generalized momentum, which is dou L by dou qk dot, becomes dou T by dou qk dot, where T is the kinetic energy. Dou T by dou qk dot. Now substitute the value of pk in the Hamiltonian function. What happens to this Hamiltonian function h? H is actually sum over k pk qk dot minus L. Now we have pk is equal to dou T by dou qk dot. Okay. Now this h, that is equal to dou T by dou qk dot. Then the second term is qk dot minus L. Now what is the first term? Sum over k dou T by dou qk dot into qk dot. What is dou T by dou qk dot into qk dot? Now we have to find out what does this first term indicate. Sum over k dou T by dou qk dot into qk dot. Okay. To understand the concept, let us consider a one-dimensional motion. Suppose a particle is moving along the x-axis. Now the kinetic energy is half m x dot square. Now take dou T by dou x dot, that is mx dot. We are simplifying the situation to understand the concept. Take T is equal to half mx dot square, then dou T by dou x dot equal to mx dot. See, we have to evaluate the first term, that is dou T by dou qk dot into qk dot. So here dou T by dou x dot equal to mx dot. Now multiply it with x dot again. You will get it as mx dot x dot, that is mx dot square. Then what is mx dot square? That is 2 times kinetic energy. That is dou T by dou x dot into x dot is nothing but 2 times kinetic energy. So we can generalize this thing. So we can say dou T by dou q k dot into qk dot, that is nothing but 2 times the kinetic energy. So the first term, that is sum over k dou T by dou qk dot into qk dot, is nothing but 2 times the kinetic energy. This is also an important relation. Therefore, your Hamiltonian becomes h, that is equal to, the first term become 2t. Let us write it one more time, that is sum over k dou T by dou qk dot into qk dot minus L. The first term is nothing but 2t minus L. What is L? L is T minus V. So this h, that is 2t minus T minus V, that is simply T plus V. What is T plus V? It is a sum of kinetic energy and potential energy. That is the total energy. Thus, we can conclude that if the potential energy does not depend upon the velocity, then the Hamiltonian that represent the total energy. That is a Hamiltonian that represent the total energy. Just like the Lagrangian T minus V, we have another relation H is equal to T plus V. And since the system we are dealing with, it is a conservative system, then this energy is constant. But we can say that the total energy of the system is constant. This is the physical significance of Hamiltonian function. H is equal to T plus V, that is equal to E. This E is conserved if the system is conservative. Now let us move to the very important section, that is the derivation of Hamilton's equation of motion. Just like we have a Lagrange's equation, we also have the Hamilton's equation, and we have to prove this. Now to derive the Hamilton's equation, let us start with the Hamiltonian function. H is equal to h of qk, pk and t. Now, what is dh? dh is simply sum over k, dou h by dou qk, dou h by dou qk dqk, plus sum over k, dou h by dou pk dpk, plus dou h by dou t into dt. Let it be equation number 1. Also, we know that this Hamiltonian function h, that is equal to sum over k pk qk dot minus L. Now from this equation we can write dh. Let it be equation number 2. And from 2, what is dh? dh is equal to sum over k pk dqk dot pk dqk dot plus qk dot dpk minus dl, that is equation number 3. Now to use equation number 3, we know what is dl. What is L? L is a function of qk dot and t. L is a function of qk dot and t. Now, in order to use equation 3, we must know dl. So let us find out what is dl. What is dl? dl is sum over k dou L by dou qk dqk plus sum over k dou L by dou qk dot dqk dot plus dou L by dou t dt. This is basically dl. Now, to simplify equation 4, use the two formulas we have already studied, that is pk dot, that is dou L by dou qk, and pk which is equal to dou L by dou Q K dot. We have derived these equations. So substitute this equation in equation number 4. Then dl becomes the first term is pk dot, then dqk, plus the second term pk dot pk dqk dot plus dou L by dou T into dt. Let it be equation number 5. Okay. Now we got dl. Now substitute the value of dl from equation number 5 in equation number 3 so that we will get dh. Then equation 3 gives dh is equal to sum over k pk dqk dot plus qk dot plus qk dot dpk minus dl. dl is nothing but, let us put a bracket, sum over k pk dot dqk plus the next term is pk dqk dot. The first term is pk dot dqk. The second term is pk dqk dot now let us close the bracket. Pk dot dqk plus pk dqk dot. Let us close the bracket. Plus dou L by dou T into dt. That plus is inside the bracket. Okay. Now if you observe the new equation of dh, we can see that pk dqk dot will cancel. From the entire equation, the pk dqk dot will cancel. So dh is equal to sum over k qk dot dpk minus sum over k pk dot dqk minus dou L by dou T dt. Let it be equation number 6. Now let us rearrange the terms. That is dh is equal to sum over k minus pk dot dqk plus sum over k qk dot dpk minus dou L by dou T into dt. Let it be equation number 7. Now let us compare our new equation, that is equation number 7, with our first equation, that is equation number 1. Compare equation number 1 with 7, equation 7. You will see that, okay, let us write equation number 1 again. What is our equation number 1? dh is equal to sum over k dou h by dou qk dqk plus sum over k dou h by dou pk dpk plus dou h by dou t into dt. This is our equation number 1. Now let us compare the coefficient of dqk, dpk and dt in both equations. In the left hand side it is dh. In both equations the left hand side is dh. So these two equations must be equal. That is only possible if the coefficient of dqk, dpk and dt are equal. It is only possible if the coefficient of each term is equal. Now first let us compare the coefficient of dqk. The coefficients must be equal, that is pk dot must be equal to dou h by dou qk. And now let us compare the coefficient of dpk. That gives to the result qk dot, that is equal to dou h by dou pk. And now let us compare the last term, the coefficient of dt, that is dou h by dou t, that is equal to minus dou l by dou t. So we have three equations, which is a first order differential equation, that is pk dot, that is minus dou h by dou qk, qk dot, that is dou h by dou pk, and dou h by dou t, that is minus dou l by dou t. These equations are called Hamilton's equations or Hamilton's canonical equation of motion or Hamilton's canonical equation of motion. And please note that it is a first order differential equation. Now consider the case, suppose the Lagrangian does not contain time explicitly or Hamiltonian does not contain the time explicitly. Then what about the third equation, that is dou h by dou t, that becomes 0, or dou l by dou t, that is also becomes 0. That is, if Lagrangian L and Hamiltonian H does not depends upon time t explicitly, then dou h by dou t, that is equal to 0, that is equal to minus dou l by dou t, that is equal to 0. Or we can simply say that the Hamiltonian is constant. We have already seen this in the previous example, that for conservative system H is constant. For conservative system H is equal to t plus v equal to E, which is constant. This happens because the Hamiltonian does not contain time explicitly. Next is an example of Hamiltonian dynamics. Let us solve, or let us arrive at the equation of motion of one-dimensional harmonic oscillator using Hamiltonian dynamics approach. The question is, write the Hamiltonian and find the equation of motion. Write the Hamiltonian and find the equation of motion for 1D, one-dimensional harmonic oscillator. We can solve this problem using Newtonian mechanics, Lagrangian dynamics, and also using Hamiltonian dynamics. In the present case, we are solving the problem using Hamiltonian dynamics. Let us start from the kinetic energy. For a one-dimensional harmonic oscillator, the kinetic energy is nothing but half m x dot square, and the potential energy, which is half kx square. Now Hamiltonian, which is generally a function of qk, pk and t. And this Hamiltonian represents the total energy, H is equal to T plus V. Now in the present case, we can write this Hamiltonian. In the present case, that is for one-dimensional harmonic oscillator problem, we can say that this Hamiltonian is a function of x and px. H is a function of x and px. Since h is a function of x and px, our Hamiltonian must contain these terms. But Hamiltonian, that is t plus v, we can write this t plus v as half m x dot square plus half kx square, since kinetic energy is half m x dot square and potential energy is half kx square. But this does not represent a Hamiltonian function, because in this function there is a term x dot, but the Hamiltonian function does not contain x dot. But instead of x dot, the Hamiltonian function contains px. So we have to write, or we have to replace x dot, or we have to write x dot in terms of px. Then only it will become a Hamiltonian function. So our first aim is to write x dot in terms of px. What is the relation connecting x dot and px? We have seen that px is equal to dou L by dou x dot, where L is the Lagrangian. What is L? Half m x dot square minus half kx square. Now px, that is equal to dou L by dou x dot, that is mx dot. Or x dot is equal to px by m. Now we have x dot in terms of px. Now substitute the value of x dot in t plus v. Then you are getting an equation that is basically Hamiltonian. Substitute x dot equal to px by m in the above equation. We have t plus v that is equal to half m px by m whole square plus half k x square. And this is nothing but a px square by 2m plus half kx square. Now this represents the Hamiltonian H. Why? Because now the Hamiltonian contains x and px. Thus H is a function of x and px. Thus H is equal to px square by 2m plus half kx square is the Hamiltonian for 1D harmonic oscillator. 1D harmonic oscillator. This is the Hamiltonian. And once you obtain the Hamiltonian, you can find out the Hamilton's canonical equation of motion, and from there you can arrive at the equation of motion for one-dimensional harmonic oscillator. Now what is Hamilton's equation? We have three equations, and let us consider the first two equation, because since the Hamiltonian does not contain time, we don't have to consider the third one. Let us consider the first two equations. Hamilton's equation of motion. Pk dot, that is dou h by dou qk minus dou h by dou qk, and qk dot, that is dou h by dou pk. Okay. Now in the present case, we can write the Hamiltonian is a function of x and px. So the momentum is px and the coordinate is x. Therefore we can say px dot, that is dou h by dou x minus dou h by dou x, and x dot is equal to dou h by dou px. And for the present case, px dot equal to minus dou h by dou x, and x dot is equal to dou h by dou px. We have the Hamiltonian H is equal to px square by 2m plus half kx square. Now find what is px dot. Px dot is minus dou h by dou x. Minus dou h by dou x means it is minus kx. Minus dou h by dou x, that leads to minus kx. Let it be equation number A. Now what is the second equation? X dot is equal to dou h by dou px. X dot is equal to dou h by dou px. That is nothing but px by m. Px by m. Let it be equation number B. Now let us rearrange equation number B, that is px is equal to mx dot. Mx dot. Now take the derivative of that. Take the derivative. When you take the derivative, it will become px dot, that is mx double dot. Let it be equation number C. Now let us compare equation A and C. A and C contains, LHS contain Px dot, but RHS is minus Kx in equation A and Mx double dot in equation number C. Therefore, from equation A and C, we can say that Mx double dot, that is equal to minus Kx. Mx double dot, that is equal to minus Kx, or x double dot plus k by m into x, that is equal to 0. X double dot plus k by m into x, that is equal to 0. This is the equation of motion of one-dimensional harmonic oscillator. One-dimensional harmonic oscillator.